Hello, everybody. Hey, this is going to be the solutions to the rotational motion quiz practice. And our first question, number one, is going to be how many radians are there in 2.5 revolutions? So this is just going to be some pretty easy review. For every one revolution, we have 2 pi. We have 2 pi radians, so that is going to be equal to 5 pi, and 5 pi is going to be 16.7 radians. Okay, you guys can double check the math there, but it's pretty easy. All right, it says how many revolutions are there in 680 degrees? 680 degrees. This is kind of going reverse, and we're going to degrees. So we know that there are 360 degrees in one revolution. So that's going to be about 1 point something. So 680 divided by 360 is going to be equal to 1.88 or 1.9 revolutions, which we obviously could then change into radians, but that's what we have it. All right, question number 3. Okay, question number 3, it says, what is the arc length of an angle of 0.5 radians with a radius of 3.2. So we're going to have here an angle of 0.5 radians, okay? And that's going to be about 28 degrees or something, but that is equal to our theta. Our radius is 3.2. And remember that theta r is equal to the arc length. And so we're going to have 0.5 times 3.2, which is going to give us 1.6 meters, is equal to the arc length. Okay. Now also remember that omega r is equal to linear velocity, and alpha r is equal to acceleration, and those would be tangential. Those would be tangential accelerations. All right. So moving on, we have question number 4. Now, question number 4 and 5 are dealing with a wheel that has a radius of 33 centimeters traveling 50 miles per hour for 10 minutes, okay? So we're going to have a few little conversion issues here, but we want everything in standard units. Okay, so this is going to be for question 4, but we're going to have a wheel, and it's going to have a radius that's equal to 0.33 meters, okay? And we're going to have 50 miles per hour. Okay, now if we divide by 2.24, we're going to get 2.24 mph is going to equal to 1 meter per second. You guys might remember that from a kind of a standard conversion that if we do the math there. So 50 divided by 2.24 means we're going to have 22.3. That's 22.3 meters per second. 10 minutes is going to be 60 seconds in a minute times 10 minutes is our time is going to equal to 600 seconds, okay? And this is our velocity. Okay, that is our linear velocity, okay? And we want to know, number 4, how many revolutions? Okay, so we're looking, you guys, we're looking for the angle, okay? And we're going to say the change in theta over the change in time is equal to omega, right? Our angular velocity. And our angular velocity is going to be equal to V over R. So if you guys, we look down here, if omega R is equal to V, then V over R is going to equal to omega. So we're going to have 22.3 divided by 0.33. And that's going to be about 67. So 67 radians per second. And that's equal to our omega. And so if we multiply both sides by t here, theta is equal to omega t, which is going to be 67 times 600. So 67 times 600, and that's 40,200. Okay, 40,200 radians, 40,200 radians. Now, you guys, we wanted revolutions, so we are going to divide that by 2 pi. So divided by 2 divided by pi. And that's going to basically be 6,400 revolutions. 6,400 revolutions. Okay, that's 6398. We're going to round that up. So that is question number 4. Question number 5, same information. Calculate the average angular velocity for the wheel. And we essentially did that. And that was 67 radians per second. 67 radians per second. And there we go. 4 and 5. All right. So moving on to question number 6. Okay. For the next 2 answers, we're going to have a pulley that is rotating at 30 RPMs and it slows to a stop in 42 seconds. Calculate the angular acceleration of the pulley. Okay, first of all, we want to convert 30 RPM into radians per second to get it into standard units. So 30 revolutions per minute. And for every 1 revolution, we're going to have 2 pi radians. And for every 1 minute, we're going to have 60 seconds. So this 30 over 60 is going to be a half, and 2 divided by half is 4. So we're going to have 4 pi, which is going to be about 13. So 4 pi, 12.6. So 12.6 radians per second. Okay, so that is our initial omega. That is our initial omega. Obviously, our final omega is 0. And we're going to have a time here of 42 seconds. Where is my thing here? And so our time is 42 seconds. And now what we're looking for here is our alpha. So there are, remember, those 4 kinematic equations are going to be translated into the angular sense. And one of those, which is what we're going to use, is omega final is equal to omega initial plus alpha t. So we're going to say omega final minus omega I is divided by t is going to give us alpha. Okay, and this is going to be 12.6 negative divided by 42. And our alpha is going to be, let's see, divided by 42. It gives us 0.299 or 0.30. Negative 0.30 radians radians per second squared, and therefore we have our angular acceleration. Now, how many revolutions does this go through? Which is going to be question number 7. So we want a theta, and we have an alpha, and we have a time. So this, remember, equated to the second kinematic equation. So the third kinematic equation would be theta is equal to omega I t plus 1/2 alpha from alpha t squared. Okay, so we're going to have this one, which is going to be 12.6 times 42 seconds, okay, plus 1/2 of negative 0.3 times 42 squared, and that is going to equal to our theta, okay? So 42 squared times 0.3 divided by 2, that's 264. And then we're going to take 12.6 minus or times 42. Sorry there. Okay, so that's going to give us 264. Okay, let's just double check that. 12.6 times 42, 529 minus 1/2 of 0.3 times 42, minus 0.5 times 0.3 times 42 squared. 264, 267. So sorry, 265. Okay. So now our answer here is 265, but that is radians. And the question was asking for how many revolutions. So we're going to take 265 divided by 2 pi. And that's going to be 42.1 revolutions. So 42 revolutions. Now remember, be careful when you are, be careful when you are doing that. When you divide by 2, if you say divide by 2 pi on your calculator, it's going to divide by 2, but multiply by pi. So you either got to put in parentheses or go divided. Okay. All right. I am going to take a quick break here, erase the board, and then we'll continue. All right, ladies and gentlemen, we're back with problems 8, 9, and 10. Now with 8, 9, and 10, they're talking about a wrench, and this wrench has got a force of 17 newtons applied from the edge at an angle of 37 degrees with respect to the radius of the lever arm. Okay, calculate the torque applied by the force at the end of the wrench. So you guys will probably remember that torque is equal to R cross F, which gives you a more complicated, solution with matrices, which we don't have to do here. So remember this is going to be F R, and what we want here is we want the perpendicular. It's force times the perpendicular radius, which is going to be F times R. Now, remember, if we look at this angle, right, we want the one that is going perpendicular to that. Okay, so it's going to be this side. So our we want the, if this is 37, we want the opposite side. So it's going to be sine of 37, sine of 37 degrees. Okay. So our force is 17. Our radius is 25 centimeters. We're changing that to meters, which is 0.25 times the sine of 37, which is about 0.6. Sine of 37. So this right there is about equal to 0.6. So we're going to have, well, let's just do it on our calculator to make it faster. 17 times 0.25 times, make sure you guys are in degrees in this case. So it's going to be times sine of 37, and we're going to get 2.5577. So we're going to call that 2.56, and that would be meter newtons. Okay, so our torque would be meter newtons. Now, you guys, is that positive or negative? Now, you can decide which direction is positive or negative, but remember that when you are talking about rotational stuff, your two directions are going to be clockwise or counterclockwise. So this is obviously going to be counterclockwise, and you can kind of call that whatever you want. All right, now what we're going to have here is what is the torque that is going to be applied to the nut here, okay? And the torque is going to be the same. The torque is going to be the same, but the overall applied force is going to be less, okay? So, and that's the beauty of something like a wrench or a lever, is that the torque, the force times radius, is going to be the same no matter where you do it. But as the radius gets smaller, the force has to go up. So essentially what we're doing is we are multiplying the force. So our question number 8 and 9 is 2.56. 8 and 9 is equal to 2.56. So now we're going to have force times radius is going to equal to 2.56. And so now when we look at the wrench, this is going to be a bolt or a nut that is 22 millimeters wide, right? So if it's 22 millimeters, okay, then we can kind of think of this part right here as being 11 millimeters. And since this is a hex nut, then we're going to have this angle right there is going to be 60 degrees. And we are looking for this hypotenuse right here. So we're going to say 0.011 divided by the cosine of 60 degrees. 0.011 divided by the cosine of 60, and sorry, we wanted that to be the sine, not the cosine. 0.011 divided by the sine of 60, which is 0.0127. Now, you guys can see there that I told you that the effective radius of the nut was 12.7 millimeters. And that's because when you apply that force is being applied here from this edge down to the radius. So it's not 11, it's going to be 12.7. Okay, so now we're going to have our effective force is going to be 2.56 divided by the radius, which is 0.0127. because this was Newton meters. This is 12.7 millimeters, and therefore those m's are going to cancel out. So we're going to get our 2.56 divided by 0.0127, and we're going to get a whopping 202, okay? So our force is equal to 202 newtons, okay? So we'll just probably call that 200 because our significant digits are only two significant digits. No, it's actually three significant digits. So we can call that 202. 202 newtons is going to be that effective force there. So you can see how a wrench is going to multiply your force because whatever torque you put out here is going to be the same torque there, but since it's a smaller radius, it's going to be an increased force. All right. So question number 11, okay? And with question number 11, we're going to have a pulley, okay? And on this pulley, we're going to have a mass. So the pulley has a mass of 2.0 kilograms, and the pulley, or the mass at the end of the string connected to the pulley, is 1 kilogram. And we want to determine the moment of inertia of the pulley. So question number 11. Now remember that the moment of inertia is equal to the sum of the mr squares, but also remember that there is a list in your book. And in there, it's going to say a solid disk is going to be 1/2 mr squared, and that is the I for a solid disk. And we're just going to apply the formula there. So we are going to have a radius of 0.15. Okay, so this is going to equal to 1/2 of 2 times 0.15 squared. 1/2 of 2, 15 squared, or 0.15 squared is going to be 0.0225. So our I here is going to equal to 0.0225, and that's kilogram meters squared. And this is going to come into play as you guys have anticipated. And I just want to double check that. So we're going to have 0.15 squared, 0.0225. Okay. What is the tension? What is the tension in the rope? All right, so we need to draw a free body diagram. Okay, so right here, okay, we're going to have this mg going down, which notice would be 1 times 9.8, which is 9.8 newtons. And then we're going to have this would be the tension up, okay? Now, you guys, I'm going to call clockwise to be positive. So we're going to say the sum of the forces is going to equal MA, and that is going to be 9.8 minus tension is equal to 1 times A, which is just A. Okay, so we do not know tension yet, and we do not know acceleration, but we are getting there, okay? So we are getting there. Let me straighten this up for us. Okay, so that looks better. All right, now the other thing we're going to do is we want to know the free body diagram right there. But because this is rotating, right, we're going to have the sum of the torques, and the sum of the torques is going to be force times radius, okay, which is going to be this tension times the radius, okay, because this is pulling If this rope is pulling, we're going to get a 90-degree angle. So this is going to be tension pulling down times the radius, okay? Now, you may remember that this torque is also going to be equal to I alpha. That torque is going to be equal to I alpha. And that is going to be I and alpha R is equal to acceleration. So if acceleration is going to be equal to A over R, so we can put A over R here. And now, where do we go here? So we know, you guys, we know what our I is, and that was 0.0225, 0.0225. 1 second here, I'll be right back. All right, sorry about that. So you guys, we know that our I is equal to 0.225, but I'm just going to put in this equation again here, and we're going to put the tension, which is a force, times R, which is equal to 1/2 mr squared, and that alpha is going to be equal to A over R. And now we can see that these R's are going to cancel each other out. And so our tension is going to equal to 1/2 of MA. And remember, our mass was 2, okay? So that means our tension is going to equal to our acceleration, okay? And so now we're going to take this tension, which is equal to A, and now we're going to say from here, we're going to have 9.8 minus A is equal to A, 9.8. We're going to add the A to the other side. We're going to get 2A, and therefore A is going to be equal to 9.8 divided by 2, which is 4.9 meters per second squared. Okay, so that is going to be the acceleration, and therefore we have their acceleration is equal to the tension. So the tension is going to equal to 4.9 newtons. Now you may kind of question this because I just have A, but remember this was really equal to MA, but that M was 1, right? So the units A times 1 gives us our tension, and then the units are correct. It's just that the number is the same. Okay, so we now want to calculate the angular acceleration. So our angular acceleration is going to be our tension, 4.9, times our radius, which is 0.15, divided by our I, and our I was 0.0225, okay? And that is going to equal to, so this, notice here, this is T, our tension times radius divided by I, and that is equal to our alpha. And so we're going to have 4.9 times 0.15 divided by 0.0225 gives us 32.67. So our alpha, we're going to call that 33 radians per second squared. Okay, and that is going to be, so this is going to be number 13. Number 12 is going to be that. Number 14, actually, we already calculated that. So 14 is 4.9. And now we want to know how long it would take to drop 1.6 meters, okay? So essentially, we've changed this stuff into linear, and so now we can even go way back into our distance is equal to our initial velocity times time plus 1/2 AT squared. So our distance is 1.6. That goes away to 0. 1/2 of 4.9 times t squared. So we're going to have 2 gets multiplied, 4.9 gets divided, and then we're going to take the square root. Okay? So that's going to be the square root of 3.2 divided by 4.9 is going to be equal to the tension. Okay, so 3.2 divided by 4.9 square root is 0.81 seconds. So our time is equal to 0.81 seconds. All right, and that is question number 15. Now, it says this next one, it probably should be on the next step. It should be using calculus to determine the moment of inertia of a rod rotating 1/5 away from the axis of rotation. All right, so I'm going to erase and set this up, and we'll talk about this. All right, question number 16 is we're going to have a rod, okay, and we want to know what the moment of inertia is if it is going to rotate about a pivot point 1/5 the way from one end, okay? So that means we're going to go from negative L over 5 to positive 4L over 5. So basically negative 1/5 to positive 4/5. Now, our equation, our calculus equation for determining the moment of inertia, as you may remember, was r squared dm. So if you just look at the units there, it would be kilogram meter squared, which is still the same thing. All right, so in a very similar fashion to calculating the moment of inertia using calculus, we want our linear density, So we know the overall length here, okay, is going to be 1L, and we know the overall mass would just be M. And again, we're talking about a uniform rod here. And so our linear density is mass divided by length. It's just like the volumetric density, it's just mass over volume. All we're doing is just changing it to length. Presumably here our width and height would be similar, and therefore they would end up canceling out anyways. Now this is also equal to a short little section, which would be a change in mass, and the width of that would be a dr. So the linear density would be equal to dm over dr, and therefore we can now say that that linear density is m dr over L, and now that is equal to dm. So now we can take this and replace it there. And now we're going to get the integral of r squared times m dr over L. Let's make our r's a little bit better here. This is a dr. Now mass over length are going to be constants, so they're going to go to the outside. And so now we just have the integral of r squared dr. And we know that that is going to be r cubed over 3, evaluated from negative L over 5 to positive 4/5 L. And we're going to end up multiplying that by m over L. Okay? So when we evaluate this, we're going to have 5 force L cubed, okay, is going to be 64 L cubed over 125, okay, minus 1 L cubed over 125, which is going to give us 65 over 125 L cubed. We multiply that by our constants. One of those L's is going to cancel each other out. And we're going to get 13/75. Oh, we forgot to divide this by 3. Divide by 3. Divide by 3. This reduces down to 13/75 ml squared. Okay, now since I did not give you any specific information such as the length and the width, that means this is going to be our formula. Now, you guys, this formula is going to come into play, I believe, in question number 22 on the rotational quiz practice. So you're going to end up using this equation for that problem 22 on the next review. So just remember that, and I will talk about how you got that when we get to my YouTube review of that. Okay, so now we are going to move on to the next page. All right, and now it says using the parallel axis to determine the moment of inertia of a 5 kilogram sphere with a radius of 10 centimeters connected to an 80 centimeter 1 kilogram rod rotating about the end. So we're going to see the diagram here. So now we're going to do this kind of one of two places. So first of all, we're going to have this rod. We're going to have this rod that's going to rotate back and forth from point A, and that is a 1 kilogram rod. Okay, and the length of this is 0.8 meters. 1 kilogram, and this would be the I for the rod. Remember, it's rotating about its end, and that equation would be 1/3 ml squared, 1/3 times 1, 1/3 times 1 kilogram times 0.8 squared, and 0.8 squared divided by 3 gives us 0.213. So the I for the rod part is 0.213. Now, if we want to calculate the moment of inertia of this sphere, we've got the sphere there at the end, and so this I is going to be the I center of mass for the sphere plus md squared, which is going to be this distance, which is the distance of offset. Okay, so our equation for calculating the moment of inertia of a sphere is listed in your book 288, I believe, or 248. Can't remember now. So we're going to have 2/5 m r squared. So that's going to be 2/5 times 5 kilograms times the radius of that is 0.1 times 0.1 squared. So obviously the 5's cancel out, and so this part of it is 2 is going to be 0.02. So this is 0.02, 0.01 times 2, 0.02. Plus we're going to have 5 times the distance here is going to be 0.9 squared. Because remember, this radius right here was 0.1 plus our 80 centimeters gives us a total of 0.9 meters or 90 centimeters. Okay, so we're going to say 0.9 squared times 5 gives us 4.05. 4.05 plus 0.02, which our I there is going to be 4.07. And we're going to add this to this 4.07 plus 0.213, and that's going to give us 4.28 kilogram meter squared. Okay, so that is our total I there. Now, if we just, you guys, if we just did mr squared, right? If we ignored this 1 kilogram and just talked about this 5 kilogram being 0.9 meters away. So we can say 5 times 0.9 squared, and now we're at 4.05, okay? So we can see, because this mass is kind of far away, then essentially, it's that mass, the greater the distance from the axis of rotation is going to make a much bigger difference in the total I. So if we just add that to our original 0.213, now we're at 4.26. So we can say that this part right here, we could essentially ignore. So the moral there is, if we have a mass that's kind of farther from the axis of rotation, okay, then the center of mass moment of inertia of the object becomes less and less important the farther it is displaced, from the axis of rotation. That's why when we're calculating the moment of inertia of, for example, a planet or something, we don't really have to worry about the fact that the planets are spheres, because we can just think of it as a mass and the distance being center to center. All right, so that is question 17 and 18. Determine the center of mass. Okay, 18. Now the center of mass, okay, from that axis of rotation, X center of mass is going to be M1 x1 plus m2 x2 divided by m1 plus m2. Obviously here, if we had more objects, 3, 4, and 5, they would just continue out, okay? So our first mass is 1, which is the rod. The center of the rod is going to be in its geometric center, which is going to be 0.4, okay? Plus mass 2, which is going to be 5, and the center of mass measured from up here is going to be 0.9. And now we're going to divide that by our total mass, which is going to be 1 plus 5. 1 plus 5. So we're going to have 0.4 plus 0.45, which is 0.85 divided by 6. And that is going to be 0.14. 0.14 would be the center of mass. Let's double check that. 5 sorry, this is 4.5 plus 0.4 divided by 6 is 0.82. Okay. X center of mass. Okay. That makes more sense because most of the mass here is far away. So I called that 0.45 and it was 4.5. Okay. Anyways, I correct it. We've got a center of mass of 0.82. Now, in that last section on the next review, you're going to also have a center of mass calculation. So you're going to go back and review that. All right. Now, question number 19 through 23. I am going to erase the board and we will then get to that. All right, ladies and gentlemen, we are back with 19 through 23. And so what we have here, and although I didn't draw it very well, we're going to have a solid sphere that has a mass of 1 kilogram, a hollow sphere that has a mass of 1 kilogram, a solid sphere that has a mass of 2 kilograms, and then we're going to have a disk that is 1 kilogram. So essentially what we have here, ladies and gentlemen, as we come down, I'm going to kind of draw it over here. So up here, we're going to have the only kind of energy that we have up here is going to be mgh, because they are not moving in the beginning. But once they roll down to the bottom, right, the mgh goes away, and we're going to turn that into kinetic energy, which is 1/2 mv squared, but it's also rolling. So it's also going to have 1/2 I omega squared. Okay. So we are going to, we're going to kind of look at this real quick, and we're going to start with A, which is the 1 kilogram solid sphere. So we're going to have mgh, and this is going to be h, and that's going to be h, and that's going to be 1/2 mv squared. Now this 1/2 I omega squared. Now the I of a solid sphere, is 2/5 mr squared. That's page 278 of your textbook. So that's going to be 2/5 mr squared. Okay. And now we're going to have our omega. But remember, omega is equal to V over R. Okay. So omega squared would be V squared over R squared. V squared over R squared. Now we can see that our radius, our radius disappears. And we can also see that our mass is going to cancel out. Now, for the case of the solid sphere, okay, we're going to have this too. So we're going to have 1/2 V squared plus 1/5 V squared. 1/2 is equal to 5/10 plus 2/10 is 7/10. Okay, so we're going to have 7/10 V squared is equal to GH. So we're going to have 10 divided by 7 square root. Okay. So our velocity here is going to be the square root of 10 GH over 7. Okay. Now, if we now move over, you guys, this was for A, right? That was for A. And we can see for C. So even though the mass of C was 2, the masses cancel out, as do the radius. Okay. So we know that the velocity is going to be the square root of 10/7 GH. Do we know what the H is? And the answer is we don't know, right? But it's all going to be relative, so we'll get there. So you guys, now we're going to change things up, and we're going to talk about the hollow sphere. And if we look up the equation for this hollow sphere, that is going to be equal to, okay, same equation here, except it's going to be 2/3 mr squared, 2/3 mr squared. So the only thing that I am replacing is the 2/5 with the 2/3. So the r squares cancels out, the m squares cancel out. So now we are going to have 1/2 plus 1/3. Okay, 1/2 is 3/6 plus 1/3 is 2/6, which is going to give us 5/6. Okay, so now our velocity here, our velocity of the hollow is going to be the square root of 6/5 GH, 6/5 GH, and when we do the disk, okay, the disk is going to have an I, okay, that's just going to be mr squared, okay, and now we're going to have 1/2 plus 1/2 is a whole, so that means we're just going to have the square root of GH is equal to the velocity of the disk, okay? So the GH is going to be the same, okay? So we have the square root of essentially 1.2. We're going to have the square root of 1.2, and we're going to have the square root of 1, okay? And so the we're going to see there that we're going to have the square root of this one's going to be bigger than this one than this one. Okay, so we want to determine the velocity of each, okay? Now, you guys, essentially, since I did not give you any height here, okay, this would be on the sphere. Therefore, these are going to be the answers. Those are going to be the answers to your velocity, okay? And to calculate the acceleration, is also going to be a little bit tricky because I did not give you I did not give you any information on here. But if we just think about gravity right here, right? So this would be gravity going straight down. So if this would be height, then this would be length. We want this component. We want this component right here. So if this is our angle, okay, then our acceleration would be equal to g sine theta. So g sine theta is probably going to be good enough for your answers. So g sine theta is going to be your acceleration for the acceleration down the ramp. That's if it's going to be sliding, and if it is not, okay, we can essentially say that v final minus v final squared minus v initial squared divided by 2d is going to be equal to your acceleration. Your initial velocity was going to go away, okay? And your d here, okay, this would be that length d, and that would be equal to the square root of h squared plus the length squared, okay? That would be equal to d. But again, I didn't give you h and I didn't give you length there, so you could leave it in this case. So it would be 2 times, and notice that you could plug that in there. But your velocity squared would just be for the solid disk would be 10 sevenths, which would be 1 3/7. So 1.42. So this would be 1.42 divided by 2. And if you just call that D, which is the length of the ramp, that would be fine because I didn't give you that. And then you could do the other ones for that. Okay, which object has the most mechanical energy? Now, the one that has the most mechanical energy is going to have the one that has the highest moment of inertia, okay? So remember that the moment of inertia, because this right here, when we combine them, right, is our disk. You guys, our disk is going to have the highest moment, the hoop is going to have the highest moment of inertia because it's just going to be mr squared, where the hollow sphere is 2/3 and the solid sphere is 2/5. So the reason that it is not going to be the fastest is because essentially it has got more moment of inertia to make it go down the ramp. Okay, so it's kind of like pushing a heavier object. It is going to take more energy to push the heavier object. So that is the answer to 23. Okay, so you guys, I'm going to set up for 24 and then we'll kind of finish up. All right, ladies and gentlemen, question number 24 is a cross product. So remember, torque is equal to R cross F. And if you have that in the IJK notation, it's just going to end up being a matrix problem. And because we only have I and J and not K, it's really just a simple 2x2 matrices. So I set this up where this is our R, which is 3, 4, and our F, which is 5, -12. And now we're going to say 3 times -12 is -36. So this minus this, which is going to be -20, which is going to give us -56. And that would be meter newtons. And that would be our torque. And remember that this, if you go I and J, then the direction of that is going to be in the downward direction, and remember the right hand rule. So we're going to say R cross F, and we're going to get -56 Newton meters, and that is problem number number 24. Now, you guys, number 25 is a review question, essentially the same as we had in one of our questions of the day. We're going to have a 0.25 a 0.025 kilogram bullet, and we want to know what's its velocity, is going to be, which is going to give us the minimum velocity needed to topple this over. So I think I'm going to need more room, so I'm going to erase our cross product there, and I'll be right back. All right, sorry about that. Hey, I had interrupted and had a long conversation, so this is about an hour or so later than when I stopped this. All right, so we've got a question that's very similar to one that we had, except we're going to have more numbers here. So we're going to have a bullet that is going to go and it's going to hit this block, and we want to know what the minimum velocity of that is to topple it over. Okay, so there's 2 components here, and this is very much like the the ballistic pendulum, where we have the bullet go into the block and then it swings up, right? Very similar to that. So we had two components then, and now we have two components for this one, except the first part is going to be angular momentum, okay? So the angular momentum initial is going to equal to the angular momentum final. And for the velocity of the bullet, now remember that momentum is going to be mvr sine theta. MVR sine theta. So now remember, when it comes in here, the only radius that we're concerned about, or this r sine theta, is going to reduce to whatever this radius is, and this was 18 centimeters because the bullet hit 18 centimeters above, okay? And so what we've got here is we're going to have V times 0.025, which is the mass, and the radius is 0.18, okay? So the angular momentum afterwards, okay, is going to have this rotation, which is going to be I omega. Now, to get the I, now the I on this was a little bit weird, and the last time we had all formulas, but now we can put in these numbers. So now, if you look on page, whatever it is, 278, okay, you're going to get an equation that's this is for essentially a rectangle that's going to rotate about its center, and which is going to be 1/12 m times a squared plus b squared. But since we have a cube, this is going to be a squared. And we're going to have plus md squared, okay? And this, so what's going to add these up? We're going to have 1/12 of 5 times 2 times 0.2 squared, 20 centimeters, okay? Plus 5 times, now the distance, right, is we want to know this distance right here. So half of 20 is 10 and 10. So this length right here is going to be 14.1 centimeters, or the square root of 2, 1.41 times 0.1. And that's going to be 1 or 0.141. Okay. So if we calculate that, we're going to have 0.2 squared times 2 times 5 divided by 12, 0.033 plus 5 times 0.141, and gives us 0.74. So our I here is equal to 0.74. Okay, so now we know that this is going to be 0.74. Okay, 0.74. Okay, now we need to know omega. Now remember, there was two parts. There was conservation of angular momentum, and now we're also going to have conservation of energy. So what's going to happen is once this bullet hits, right, we are now going to give the block angular rotation. So it's going to have angular velocity. So that's going to be 1/2 I omega squared. And what we've got to do for that minimum velocity is we've got to get this block to rotate up, which is going to now give it mgh. Okay, so that minimum velocity, what would happen is this rotation, it would kind of bring it right to the top there, and minimally it'd just be a tiny bit more, and then it would topple over on its own. So there would be no rotational kinetic energy here at the top. Now there is mgh on this side, there would be mgh on this side, so this is really mg delta h. All right, so now we want to know, okay, the difference in height between this. Now once it rotates up, this is still 0.141, and this is 0.1, so this change in height, the delta h, is going to equal to 041. Okay. And we are now going to say that we're looking for omega. So omega is going to equal to 2 mg delta H divided by I. And then we're going to take the square root of that. And that's going to be omega. That's going to go there. And then we can solve for the velocity. Okay. So that's going to be the square root of 2 times 5 times 9.8 times 0.041 divided by our I, which was 0.74. And then we're going to take the square root of that whole thing. So 2 times 5 times 9.8 times 0.041 divided by 0.74, and that's 5.42. We're going to take the square root of that, and this omega is going to be 2.33. So now this answer right here is going to go there, 2.33. And now we're going to divide by 0.025 and divide it by 0.18. And now we have our velocity. So we got 2.33 times 0.74 divided by 0.025 divided by 0.18. And we have 383 meters per second. Okay, so our minimum velocity was equal to 383 meters per second. Okay, and that is the answer to 25. Now, you guys, besides this would be a pretty complicated question to ask you on the quiz, but I might shorten it and give you all that information, give you the I and give you that sort of stuff, and then ask you to calculate it. So you don't have to end up doing this, and you don't have to end up doing some of the other stuff. So it's just going to be more of a straight in, do you understand that problem? Okay. Now, for our last three questions, we essentially are going to have this person, okay, and they're going to have their arms, they're sitting in a chair, okay, that is going to be able to rotate, okay, and they have barbells kind of at the edge there. And then what they're going to do is they're going to have this barbells, and now they're going to bring these barbells closer into their side. So what we have here is a conservation of momentum issue here. So we're going to have I omega is equal to L. So our initial is going to equal to our final. Okay. And what we want to know, calculate the final angular velocity right there. If we have the initial is 0.625, and the I for this one is going to be mr squares. This is going to be for the barbells, plus the person and the chair. Okay, now I told you that the person in the chair, this I is going to equal to 3.2. So right down here is going to be 3.2 plus our mr squares. Okay, now the arms extended is going to be 1 meter. Okay, and the masses are going to be 5 pounds each. Okay, which gives us 10 pounds. Okay, so 10 pounds, and for every 2.2 pounds, there's 1 kilogram. So we're going to say 10 divided by 2.2 gives us 4.5. So we're going to have plus mr squared, which is going to be 4.5 times 1 squared. Okay? So whatever that is, which is going to be plus 3.4. So we're at 7.9. Okay? That's our I. This omega was given in the problem at 0.625, 0.65 rather, okay? And this is going to equal to the I here, which is again going to be 3.4 plus our mr squared. And when those 10 kilograms get moved in, okay, they're going to go from 1 squared to 4.5 times 0.25 squared. Okay, so when those barbells come in, now they're only going to be 0.25 meters from the center. So 4.5 times 0.25 squared is 0.28 plus 3.4, and that is going to be 3.68 omega final, 3.68 omega final. So we're going to divide this by 3.68, right? So all of this gets moved down to there. And now we can multiply and divide all that. And we are going to get 1.4. Let me double check that. 7.9 times 0.65 divided by 3.68. Okay, so that's 1.4. So we're going to go, so our omega, and this is problem number 26. And omega final is going to equal to 1.39 radians per second, 3.9 radians per second. Okay, so now find the change in kinetic energy. Now, our kinetic energy, and you guys, I'm going to do this up here. Our kinetic energy is 1/2 I omega squared. 1/2 I omega squared. So initially it's going to be 1/2 times 7.9 times 0.65 squared. Okay. 0.5 times 7.9 times 0.65 squared. So that is a kinetic energy of 1.67 joules. And now this was initial, so our final is going to be 1/2 I omega squared, which is going to be 1/2 of 3.68 times 1.39 squared. Okay, so 3.68 divided by 2 times 1.39 squared, that's equal to 3.55. Okay, so this is what the kinetic energy final was. This is the kinetic energy initial. Subtract 1.67, and we're going to get the change in kinetic energy is 1.88. We'll call it 1.9 joules. That is question number 28. Find the change in kinetic energy, if any, from the beginning to end. And finally, 28. How much work did the student do to bring the weights closer to them? If you were sitting in there, it would take energy to do that. But remember, work is equal to the change in kinetic energy, which would be 1.9 joules. Okay, so that is the answer to both 27 and 28. Sorry, this took so long, but there you have it. All right, take care, and we'll see you next time.